And then the last one, and one of the most important, is the .gbk file, also called gene bank file. Here you have a combination of everything. You have all the genes there, you have their sequences, and you have also annotations in which position, even in which position they are in the genome. Okay, this is a really important file because when you are submitting a genome to the NCBI, sometimes you need to submit also this file of your genome. But also, the NCBI have their own tools to obtain these files from your genomes. So now, as Victor said, you cannot trust that much all the annotations, right? So what you have to do is annotate it with all the database that you can to contrast and cross-link the results of the different annotations. So one that is really nice to use and really easy to use is the eggnog annotation. Why? Because the eggnog annotation is really simple. You just give it the .faa file from Proca, and it will annotate you with database as the ones that Victor mentioned as PFAM, KEGG, COG, and multiple more. Also, it's really easy to use, and it has a web server version where you can just upload your FASTA sequences, and it will tell you a functional annotation about them. But for now on, in this analysis, we're going to focus in the COG annotations for limitations of time, okay? So we like the COG annotation because, as Victor said, this COG database is aggregated in general functional annotations. So here we can see a bar plot where we have in our x-axis or different bacteria. We have the two in the right are the one that we saw an antagonist phenotype, and the one in the left is the one not. Then in the y-axis, we have the relative abundance of COG functions or COG categories. So each color will be like one COG category. So already you can see that our two bacteria that has the antagonist phenotype have a similar pattern of colors, right? So that's already telling you something, that these two bacteria are more similar than compared to the other one. So if we look more in detail, we see that in this change of pattern, we see that this purple section or category that corresponds to Q or secondary metabolites is more abundant than in the bacteria with an antagonist phenotype compared to the one that not. So you are already thinking, okay, maybe it will be something dealing with secondary metabolites. But okay, we are going to continue with the comparative genomics analysis. So, well, also you can, sorry that I forgot, before I forgot, if you go in the R studio, in the R file, to the code lines 181 to 189, and you press play, you will generate this plot. So let's try, and please say if you have any problem. Okay, we cannot spend much time because of limitation of times. So you will just see this plot in your screen. So, okay, we are gonna move on. So, okay, let's wait 1 minute more. I'll let everyone have the plot in its own computer. It's always nice. Yes.
We have installed ggplot2 instead of ggplot. That's why showing it error.
Yeah, then you need to install. Do install dot. But maybe you have it installed and you didn't. You do library.
I think if you want to reproduce this, you need to install ggplot as well.
Okay, wait. I think I forgot something. If you go to the first part of the code, you will see a region that it says library and a lot of packages. It's because we forgot to load the packages. So my mistake.
So go to the beginning. So you go to the beginning.
¿Sabes qué? Which lines are? 18 to 24. So if you go to the lines 17 to 24 and you run that chunk of code, you will load all the packages, okay? That I forgot to mention that. Yes?
Here. And then
There's an error here.
scripts, the library.
You click here, you load the packages.
There you go.
Click there.
And then now you can run it, I think. Are you there?
Okay.
Yeah, now try to run it. The code.
Because
Try to
we
run the
say
code.
error,
Yeah, the libraries are
object to
loaded.
plot not found.
So now you need to run the code. At the line 181.
Okay. Yeah,
Yes.
found. Function. Well, I don't know that, but don't worry. Like for timing, we don't have it. Sorry.
I know it's running.
Mm-hmm.
It says here, stop.
She's getting this one, but she has all the packages.
Yeah. So they got the same, but I don't know what it is.
Yeah, and I'm looking for the function in R, but it doesn't say any package. It actually
Yeah,
doesn't.
but a lot of people it work. It will be loaded. Porque no ha cargado el environment. I know sir, you need to load the environment first. So you go to files, you need to first unzip this. You need to unzip. You see that it's .zip. You need to extract that in your folder, not the zip one. You need to unzip it and load the environment. All good here? Mm-hmm. Yeah.
Yeah, I don't know what's going on here.
Go to our studio. And it's a different function that you didn't. You clicked here in the dot array. Click yes. Now run it again. So yes, and now run it again. So you just there, and then you go to plots, and bam. No worries. Ooh, what's that?
Very interesting.
Yeah, you load everything.
What if you do zoom? What happens?
You click in. Oof, nah, that's weird. I don't know what even that means. Mm-hmm.
since we are proceeding with this, now I want to take first some 10 genes. Is there any to pick like that for RNA interference?
You can ask me this after the practical, and I will tell you, okay? Detail of the environment.
It's like something with the it worked, but then it's not popping the figure. Do you think that it's something with aesthetics or
Yeah, because she's not running the
181, right?
yeah, here, but she didn't run the whole thing.
I know.
She just ran one line. Oh no. What? What? I think you delayed half of the chunk, maybe by accident. Because now the plot thing is not there and it should be there. So maybe we try Control Z.
You got it?
Yeah, that's weird. I mean, no worry, it's this plot. You know, try to download it again. It's just so you interact with that a bit, but don't worry.
So maybe you can close
To make it wider, what do you do? You click on it or?
No, just do zoom,
Okay, so.
and then you have it. And then you can move it a bit and put it like in the proportions you want. We have to move. Thank you. Luisa, Vic, vamos. Okay. Okay, I see most of you have it done, but don't worry if you didn't manage to get it. Everything will be here, and we are just going to run a couple of more things, okay? So we come back. We got our message here. We see a bit like in a general overview of how our Koch categories are in the 3 bacteria. We see that our 2 bacteria with an antagonist phenotype have a similar pattern, and we see that this category Q secondary metabolite is in a higher proportion than in the other bacteria. So now we see, you remember these tables with 0s and 1. This is the equivalent for our analysis. So we have an absent-present table of these Koch annotations in our 3 bacteria. So if you go to the code and open Koch table, so then up in the right, you will find a variable called Koch_table. Just open it, and it will open the table, okay? This table. I think this is easy, and all of you will be done in a moment. But basically, first, please look at me, and then I will explain the table, and then you look at the table in the computer, okay? So we have Koch IDs. This is IDs of really specific functions or Koch functions. Then we have some descriptions. For example, here, this 28HB2 is fatty acid isomerase. And then here we have Koch process. This is the general functions. So when we've seen in the previous plot with different colors, each color will be, for example, one of these letters. There are a total of 24 or 24 general categories, okay? And then here we have our 3 bacteria and how many times they have that annotation in their genome, right? So then we have already enough information to perform a PANCOR analysis at the gene level. So if we move here, we have our PANCOR analysis of our 3 bacteria based on these COG annotations. So we have for 2 bacteria with a antagonist phenotype, and there in the right, or bacteria with no antagonist phenotype, okay? So remember from the beginning here, what will be the core genome? Can someone tell me? Which annotations are common in all these 3 bacteria? How many? Good, the 2,000. 2,203. But now we are interested in our analysis, right? And in our analysis, we are looking for some genes or COG categories that are only present in our phenotype, in our bacteria with an antagonistic phenotype. So how many do we have? Where are they in this plot? Can someone tell? Loud? Sorry, I will repeat the question. Okay, we have 3 bacteria, 2 with an antagonist phenotype, right? That they are in green. And then the one in red doesn't have an antagonist phenotype, right? So how many COG categories are common between the green bacteria? Okay. Really good. So yes, 144. Okay, so here we have already a small number. Well, small, it's still over 100, but we have 144. So in the lines of the code 193 to 202, if you run that, you click, the play, you will generate this plot. Okay, so let's try to do it. Good? All good? Thumbs up? Okay, good. Okay, so we want to see maybe these 144 genes more in detail. So, okay, we have our Venn diagram, and then you could subset this table and only look for the COG categories that are only present in your 2 bacteria. And then you can do something similar as we did before and plot the COG categories of what is common, of these 144 COG annotations. So we see one main color. This main color is the COG category function unknown. So this is already telling you that using these annotations, there is still a lot that is unknown. And then we have the second biggest color here, this kind of reddish purple thing. And then this one corresponds to the category secondary metabolite that we already saw it in the general one. So we are seeing already more hints in that there is something to do with this secondary metabolite category, right? Okay, so then now we are thinking, we did all this analysis and we saw that maybe this antagonist phenotype have something to do with, this secondary metabolites have something to do with this antagonist phenotype, okay? So, well, we don't have to generate the plot. So now we see, okay, we want to study secondary metabolites, right? Because it's what is important. So then we will go to an annotation that is more specialized in secondary metabolites. We did COG, that is really general. We already got the insight that there is something to do with secondary metabolites. So now we move for a more specific database that in this case we are gonna use Antismas. So with Antismas, we are gonna do the BGC prediction and annotation. So here you have a bit of overview of Antismas, but Victor in his lecture already explained in detail. And here you can use as input a file .fna, that is the genome that you got from the assembly, or the .gbk file that we saw before. You remember, right? So Antismas, one of the nice things, it gives you this output that is really interactive, and then we will see a small example thereafter. But then, okay, we have our predicted our BGCs, biosynthetic gene clusters, in our genomes. And now what we do? Well, now we cluster them with Big Escape. So Big Escape, basically what it does, it uses the input as input, the output of Antismas. So this is already telling you that all these tools, they depend in each other. So it's important the compatibility between them in bioinformatics. So, but basically what Big Escape does, it tells you the similarity between the BGCs that you found with Antismas to see how similar are to each other. So with that, we can do a PANCOR analysis at the BGC level. So this will be like another representation, like the Venn diagram that we did at the gene level, but with BGCs. So we have as rows or 3 bacteria, in green, the ones with an antagonist phenotype, and in red, the one who doesn't have an antagonist phenotype. So in the red cells, and you can see the presence of the different BGCs. So here we see the first 4 columns that are red for the 3 bacteria. So then what will be that? Anyone knows? When we say we have core genome, pan genome, unique one, what will be this? The core. So this will be the core BGCs of these 3 bacteria, or the core secondary metabolites that these bacteria produce. But then we see this region here. So we see 2 BGCs that are only present in our bacteria of interest, right? So we are like, okay, we did the analysis at the gene level, we check the genes, we see the category of secondary metabolites pop up, then we move to this framework that is more focused and more specialized in secondary metabolites, and we found these 2. So if we want to check more in detail what these BGCs do. So then we took one of them and we aligned them and we see this. We see the BGC chain, so we have each arrow is a gene, and we see that it's present in our 2 bacteria with an antagonist phenotype, right? So we see that some regions are almost the same. We see here and also there, but also other regions are a bit slightly different. But in overview, it looks really similar, right? So okay, we have this, and then we know that it's an NRPS domain because there in the program it tells you, okay, there is an NRPS here, a non-ribosomal peptide synthetase, okay? So now we want to see what it does, right? So for that, I'm just gonna get out of the presentation for a moment. Okay. So then we go to the output of Antismas. Here we are in the output of Antismas of one of the bacteria that has antagonist phenotype, okay? And this is our NRPS. So we see here all this BGC that seems that is only present in our interesting bacteria, right? So then we want to know if someone already knows what this BGC does, because maybe this BGC is already really well studied, and then, well, you can report it, but there is not that, and then you are not reporting anything novel, right? So for that, here you have this a small window called known cluster blast. And then you can check download graphic. And here it tells you the similar BGCs that they found in the database. But we see that it reports only 2 hits. Okay. Well, it reported 2 hits, but the similarity was really low. One was 7%, and the other one was like around 11%. So then you cannot say that is that BGC. You know, it's a really low similarity. So then you will say, okay, I think I found something interesting. I found these NRPS that they are famous to be involved in antifungal properties and an antagonist phenotype, but it's not reported in the database. So then maybe I'm interested in do some mutagenesis there and try again to see if this antagonist phenotype maybe is gone. And then you will have the cause of your antifungal properties in this bacteria, right? So you can see now, let's summarize a bit what we have seen. So we did the comparative genomics workflow. Let's wrap it everything. We did it first at the gene level, that is the most common, and we got our Venn diagram. We pinpoint these 144 genes. We saw that there is this secondary metabolite category that is popping up. So we see how the things are going, and then we are like, okay, now because we are interested in these secondary metabolites, we are gonna move to a more specialized comparative genomics, more specialized for secondary metabolites, and that's Antismas and big scale. And then we do our PanCore analysis at the biosynthetic gene cluster of BGC level, and we found this NRPS. Then we check in database if this NRPS is known, and then we see that it's not. So then you have there a lot to study and a lot to continue, right? So this is a typical workflow for comparative genomics. You always start general, but then depending on what you find or what you see in a general overview, you can use more specialized databases, right? To pinpoint the specific genes that could be the cause of your phenotype, okay? So now, I just want to tell you a bit of one of my PhD chapters that is called Microlife, and basically it does what we have been doing here. We have our genomes, and then we follow one path at the gene level, so we generate our table with 1 and 0 of gene families in each bacteria, and then in parallel, it does the same workflow, but with biosynthetic gene clusters or BGCs, right? But this was built for a large amount of genomes. So for example, we applied this in Burkholderia and Paraburkholderia genera. So we downloaded from the NCBI all the genomes that they were there. There were around 5,000, 4,622. And here you can see a map similar to the beta diversity that you remember from the amplicon analysis, where each dot is one bacteria, and its color is like the lifestyle of that bacteria. So we have here in this red all the opportunistic or animal pathogens. In green we have plant pathogens, and here in purple we have some of them that are beneficial or environmental. So then we check for genes that are only present in all of these plant pathogens, but they are not present in the others. And we found 723 genes that we call them lifestyle-associated genes. Then we move to the literature, so then to see if there is something new, we move to the literature validation. We do some literature validation, so then we check for already virulence markers that they were described in these plant pathogens, and we find some of them like homoserine-lactones, toxoflavin, and the well-known type 3 secretion systems. But then we also want to validate it in the lab. So we took one of the plant pathogens, bacteria, Burkholderia plantari, and we select 29 genes that we found of this list. First, we check if they grow, we mutate in the bacteria in that genes, and we check if they grow like the wild type. We see that some of them not, and then we end with 15 lags, or 15 of these genes. Then we check if they have a reduced virulence infecting rice. And we check it, and we got 5. So we are already, this work was also performed with Adrian and Kevin from our group. So we doing comparative genomics at large scale and having a good metadata, we were able to identify 5 genes that they have no function associated. We don't know what they do, but we check it and we saw a reduced virulence in rice, infecting rice. So that can tell you like all the applications of comparative genomics. So this is large scale, and I'm building it, so it's really easy to use for everyone. So then you just need to go to the NCBI, for example, and I want to do it, for example, with Pseudomonas. I just put Pseudomonas in assembly, and then you got this. That's the only thing that you need to give to the program. You give that to the program, and it will automatically perform all the workflow to generate these plots and tell you which genes are common or not between different groups of bacteria. And that's all. So any question, please?
Okay, any questions from anybody?
No questions? That means that, did you get anything?
Okay, now it's open for the Yeah, please. So the example that Guillermo just gave, for bacteria, you can do similar types of models for Pseudomonas. And when we were in the practical room, there was one of the students that said, yeah, maybe I have an opportunistic bacterium, or I think it's an opportunistic bacterium. So how can I be sure, right? So comparative genomics, like Guillermo and also Victor in the lecture today, can help you sort of like as a diagnostic tool of where does it fit. And there comes the blood.
¿Vas a hacer la network al final?
No, voy a hacer el resumen. Workflow, you need to be pretty sure what kind of lifestyle they have, right? The pathogenic, endophytic, plant pathogenic, fish pathogenic, etc. And for a number of bacterial genera, that is well described, but for a large number of bacterial genera, that has not been described properly. So the metadata that we always talk about, right? So provide a metadata where was it isolated from, what kind of traits or phenotypes are associated with that. That will help you in this type of analysis. So that's not metadata, but it's just a metadata of the isolate. And for many bacteria, like I said, that is not super well known or well described. encoding these genomes, I would say go to 5 steps. Right? So for many of the genera, there are 5 steps. So that was my 5 cents to the story.
Okay, anybody has got any clarifications or doubts? Yeah.
I need a clarification about the lifestyle associated genes. You have set of genes, how do you know one method? So you gave introduction about lifestyle associated genes. What are those?
Yeah, we basically, well, you said. Yes. So the question was, what are these lifestyle associated genes? So basically, I did a huge comparative genomics, and then we recollect, and it was not easy, you can imagine with all that amount of genomes, metadata of each bacteria. And then we saw if they were reported as an opportunistic pathogen, if they were reported as a plant pathogen, or if they were reported to be beneficial or just environmental. Then we add that, and also another thing that I didn't explain, using machine learning and artificial intelligence, we were able to assign lifestyle to some of them that we didn't know or that we couldn't get metadata from them. And then once we have the metadata, we were able to make comparison to see which gene families are present in the plant pathogens, that is the lifestyle that we focus, that are not present in the all other groups. So that our hypothesis is that, okay, if our plant pathogens, all the ones that are plant pathogens have these genes and all their cousins that they have other lifestyle, then they might be involved in being plant pathogens. So then we select some of them randomly, we mutate them, and we saw that quite good proportion, 5 out of 15, we saw a high reduction in vitamins when we still don't know anything about what that gene does.
Next question is, are we talking about all the pathogens? Can you find the amino
Okay. The question was that if they are common in all plant pathogens. Then in this study, what I was seeing is that in each genera, or in each genus, or in each taxa, they arrive to maybe the same lifestyle by different ways. So maybe there are some mechanisms involved, and we did some analysis, and there is still some type 3 secretion system, for example, genes that you will find, but maybe they are not the same gene, so in sequence, but they have a similar function. So you could see secretion systems to be important, for example, in multiple pathogens. But in each specific taxa, they have one mechanism or another.
Any more questions? Anybody? Any more clarifications?
So there were a few students that asked me for the lab protocol to make transparent soil. Right? I asked my student back home to send me the lab protocol, that a link to the paper, but just also the lab protocol itself. And I forwarded it to Mark in the chat. I already recorded, so don't worry.
Small clarification. The optimum temperature for the best growth of the bacteria. You take into account in your lifestyle prediction.
Yeah, for our analysis, we didn't take that into account, but we made the tool flexible so everyone can load their metadata and see how it distributes in this map or like the metadiversity plot that you see. So we focus in a really general like metadata, but then we also check in more specific metadata. For example, we're studying genes associated with being endophytes or other lifestyles. So at the end, you can always load your metadata and see how it's distributed in the map.
problem is that there is no metadata for all bacteria. So, and that's why it's very important to, record everything and do a good metadata file.
Even for lifestyle prediction, where do you fit the virulence factors? Many times the virulence factor in medical or disease habitat is also a biocontrol trait in some bacteria. For example, rhamnolysis in pseudomonas. It's a virulence factor. The same rhamnolysis is the Antismas compound. So where do you fit goes to the biocontrol side or it comes to the disease habitat side? Because where do you fit that? I'm sure such a phenazine is another classical example. Phenazine is also a virulence factor in Venosa, but same phenazine is a biocontrol trait in pseudomonas. So do we have any options to good phenazine, bad phenazine, something like that? Or
I guess, well, sorry, maybe, so I guess it will depend a lot on other genes that also that bacteria has. Okay, so I'm not 100% sure because, for example, I don't know about phenazines. Maybe just have more knowledge about phenazines. But for example, in the type 3 secretion system, you see that the type 3 secretion system is also present in beneficials, but they don't have the repertory of effectors. So I don't know. Maybe the pathogenic ones, they need to have the repertory of effectors, type 3 secretion system plus phenazine to do their activity, and the other ones are missing phenazines. Well, sorry, the effectors. Yeah. So it,
No, I think that's the strength of this program, so that it takes into account not a single gene, right? But it's multiple. So like Victor said, if type 3 secretion, other virulence traits are also present next to, for example, the rhamnolipid biosynthesis genes,
yeah.
then it will still fall within the category of pathogens.
good. Okay. Any more introduction from anybody? Okay. If it is not, I think in a minute for our online viewers, you can sum it up. Whatever you. Yeah, he is going to do that.
I will do it. Okay.
That is on the.
I do it here. Huh? Excuse me, Josh. It's up to you guys. So well, for me, if you want to do it, today, or we can do it on Monday, that's also fine for me, because I think Monday we will have also some time, because just to give you an idea, everything that we have talked, it's also applicable to metagenomes. So, and then I will be talking about metagenomics on Monday, and we can take part of that lecture also to do the network analysis, and then everybody at home can install Cytoscape and download Java, and I don't know, but I'm fine also doing it now. Yeah, then we do it on Monday, and then it will link quite well with the metagenomics, okay? But you already have the program, many of you installed, right? So that's already a good sign. Okay? Kumar, should I? Okay, so this one? So I'm okay for the online as well with this? Hello, online people. Yeah, good. Okay. Well, so dear online participants, so we have finished our 4th day, of course, and today we have been learning quite a lot of things, I think. We have learned about annotation tools, and we can differentiate them in 2 types, the ones that are more general and give a general overview of which genes are in a genome, and we have learned also about more specific tools that are specialized in, for example, secondary metabolism or carbohydrate degrading enzymes. We have learned the key basis for comparative genomics, some terms and definitions like, for example, PanCore, pangenome, core genome, and so on. And also, we have done a practical and several examples about how useful can be comparative genomics for the identification of genes and features involved in different phenotypes. And in the practical, if I am not wrong, in the practical, what we have been doing is transferring the fungus to the plates for the antagonistic activity assays, and we will see the results on Monday. So with this, I think I would like to close the day 4, and well, I hope you enjoyed, and have a good evening. Thank you.
He has to run here.
Oh, you have to.
That's done.
Oh, no. Okay.
Okay. Tomorrow we will not have any. It's off day for all of us, right? So convocation, and we have a. You please attend the convocation. The program what we wanted to do tomorrow is already done today. I think the incubation is done at low temperature. Shana? Yeah. So next 3 days you have a lot of work to do. The presentation that is scheduled on Tuesday. So I'm sure the weekends are completely engaged, right? So we will meet on Monday morning. Most likely we will be having the keynote lecture by those on Monday morning in one of the auditoriums in Ira, right? So we have not yet decided. So it could be any one of the auditoriums. With that,